Solving DC circuits with Kirchhoff's rules. Circuits will involve resistors or capacitors, and here are some schematic symbols that are used. Ohm's law is shown for resistors, and there's a capacitance formula that relates charge on the capacitor to volts. In DC circuits, the power supplies are constant sources, either constant voltage sources or current sources. It's also important to realize that the voltage drops as you go with the current through a resistor. However, for a capacitor, the voltage depends on the charge, which is a current impulse. For constant sources like voltage sources and current sources, it is expected that the current comes out of the positive side through the circuit and back. Kirchhoff's rules. There's the junction rule, or KCL, Kirchhoff's current law, and the loop rule, or KVL, Kirchhoff's voltage law. The current law, or the junction rule, is simply that current entering a junction must leave. So, for example, at node A, you'll see I1 and I3 are currents entering junction A, and they go out as I2 and I4. For the loop rule, we have that the sum of voltage changes going around any closed loop equals 0. It's interesting to note that the junction rule is an extension of a series connection. You'll see at junction C, the current I5 comes in and I1 goes out. So that just means that I1 and I5 are the same. And in series, we say that the flow is the same. And the loop rule is an extension of parallel connections. Our loop X, instead of going through item 4, could have gone through item 5. So we get that in parallel, items 4 and 5 have the same voltage drop. On to circuit analysis techniques. So we start with branch current analysis. And here's a sample circuit showing 5 resistors and 2 power supplies, a current source and a voltage source. First, we want to identify our nodes or junctions now that we understand that we have 7 branches, 2 power supplies and 5 resistors. So here are the nodes A, B, C, D, E. And notice that A, B, C, and E are shaded in a darker color. I like to do that when the node joins together more than 2 branches. So you'll see junction or node D is left unshaded because it joins together exactly 2 branches. The unshaded nodes, such as D, then show series connections. And so with our list of nodes, we'll start off with a node table. Next, we assign branch currents. Every branch needs to show a flow, whether we know the direction or not. Now, for the power supplies, we can take an educated guess, right? Certainly the current source on the left, we know the flow is from bottom to top, I0. For the voltage source, we would assume that current comes out of the plus, enters the circuit, and comes back in on the minus side. Otherwise, we just put an arrow in. We don't have to know the direction ahead of time. And we'll start a branch table here as well. But the rule for branch currents is that we want to reuse the same branch current label for items connected in series. And this is why that junction D being left unshaded is visually helpful, because we can see that resistor 5 and the voltage source are in series. So they both have a branch current given by the label I5. Now that we have our flow arrows, it's also important to indicate for resistors that the volts decreases as you go with the flow through the resistor. So we indicate that as going from plus to minus, going with the flow arrow. This doesn't mean that these directions are correct, but the procedure self-corrects. If we made a mistake in the direction of a flow, it will be solved as a negative value, and then we would know it should go the other way. So that's the setup steps involved in branch current analysis. On to the branch current analysis procedure. We will do this with numerical values. So you'll see the resistors R1, 2, 3, 4, 5 have ohms values. Our constant current source on the left is half an amp. Our constant voltage source towards the right near node E is 10 volts. Notice that one of the variables we will solve is the voltage drop across the half amp power supply. So even though this is called branch current analysis, the variables include unknown voltages when you're dealing with current sources. So how many Kirchhoff equations do we have to write? Well, here's a worksheet that lets us indicate the number of nodes in the circuit, and we had A through E, that's 5. How many were not shaded in, that was D, that's 1. How many nodes are shaded in? In circuits, they're often called essential nodes, and that's 4, A, B, C, and E. 1 is always arbitrary and called ground. And sometimes there's known voltages that can help us solve the circuit. In our case, we do know a 10-volt voltage source, so we have one of those. Now with our branches, we said we had 7. We're not going to discuss tree branches and chords at this time. I have another video that goes into more detail on that. But what I've called C, the chords, for our purposes, in a planar network, a network that can be drawn in the plane, we will just look at the mesh loops, and there are 3 mesh loops. We're also going to indicate that there is one known current, the half amp supply. Now for branch current analysis, we only take the number of essential nodes, subtract 1 for ground, and that leaves 3 junction rule equations to write. And for the loop rule, there's 1 equation per mesh loop, so 3 loop equations. And that's a total of 6 equations that we'll have to write. So now let's write the equations, and we'll indicate the mesh loops as loops X, Y, and Z. Now, since we only have to do the current law or the junction rule at 3 of the 4 shaded in nodes, I'm going to choose A, B, and E. Now, here are our equations. Now let's look at the current law or junction rule. Let's look at node A. We'll see that the half amp comes up and then over from left to right into junction A, and I2 comes up from E through the 8 ohms and over to the left to A. So the half amp and I2 enter junction A, and you'll see in the equation those terms are on the right, and I1 leaves junction A going through the 5 ohms, and that's on the left. So I1 equals a half plus I2. For junction B, you'll see I1 enters B, and I3 and I5 leave. That's our second KCL equation. Last but not least, at junction E, I5 enters, and it goes out as I2 and I4. Now, for the loop rule, or KVL, now I'm going to start for loop X at node C, and go over to the left, up through the half amps, and over to A. I expect to increase by the unknown volts across that current source. Then as I go from A to B down through the 5 ohms, you'll see I'm going, look at the resistor, plus to minus, going with I1. So I have a voltage drop, minus 5 I1. That's Ohm's law. I'm going to continue from B to C, and I'm going through the 3 ohms, plus to minus. Again, I'm decreasing as indicated by the plus to minus going with I3, so minus 3 I3. That equals 0. You can convince yourself that you get the equations for Y and Z, but I do want to look at the fact that in the equation for Z, the 20 I4 is a negative term, but the 3i3 is a positive term. And let's see why. The equation is written as if I went around the loop clockwise, starting at D, then going to E, which gives me the plus 10, down through the 20 ohms, and that's plus to minus, so minus 20i4. And as I come over to C and up to B, now I'm going against I3, minus to plus, so that's why I have an increase plus 3i3. And then finally from B to D, plus to minus 16i5 equals 0. And that's a lot of equations, so if we arrange these in a matrix, we can put the coefficients of the branch currents. Now I say branch currents, but the branch current variables also include unknown voltages. There's that curly E, that is the voltage drop across the half-amp supply. So in any case, I have the coefficients of the branch current variables, and that's 6 columns and 6 rows. My 7th column, RHS, is right-hand side. And if you take the 6 equations, you can convince yourself that this is how they would organize themselves. Now that's a lot of equations to solve, so we would use software like Excel. So I basically want to solve for my branch current variables as, and I have equals, and it's going to be the matrix multiplication, M mult, of the inverse, M inverse, of the coefficients of the variables, and that multiplied by the right-hand side. Remember, in Excel, array functions, you have to hit Control-Shift-Enter, and we have our solutions. Now, with our branch current variables solved, we just put those in the branch table. And now all that's left is to find the voltages associated with the resistors. We simply use Ohm's law. So now we know the volts and amps for every component in the circuit. So at this point, I'll complete the node table, choose a ground, and a ground is simply a node that you are calling 0 volts. It's a reference. So here I'm choosing node C. Any of the 5 nodes could be ground, so that's 0 volts. Now I can find the other node voltages by simply walking from C. For example, if I walk up through the 3 ohms from C to B, then the change in volts from 0 to the node voltage at B, I'm going through the 3 ohms minus to plus. That's an increase of the volts associated with the 3 ohms. And since that's 0.768 volts, that puts me at 0.768 volts as the node voltage at node B. If I continue walking straight up to A, in addition to the 0.768, I go minus plus against I1. I'm going up to A. I'm increasing by the volts for the 5 ohms. So 3.12 volts added to 0.768 gives me the node voltage at A, 3.888. And you can continue walking to D and E, starting from C, to get the other node voltages in the table. Last but not least, we can take volts times amps in the branch table to calculate watts, the power. And sure enough, the sum of the powers supplied by the sources is equal to the sum of the powers delivered to the resistances. On to loop analysis. Now for loop analysis, we actually follow the same setup steps as branch current analysis. Now how many equations do we have to write? And we have a side-by-side comparison, branch current analysis and loop analysis, and we'll see that loop analysis is much more efficient. First off, is loop analysis only requires loop rule or KVL equations. We do not write any junction rule or KCL equations. And we get to take advantage of the fact that we have a known current source, half an amp. So 3 minus 1, that's 2 loop rule equations to write. So there's a total of 2 equations to write instead of 6. So with loop analysis, the loop currents are fictitious variables that represent the number of degrees of freedom in the branch currents. We have our loops x, y, z again, but x is now a known loop, half an amp. So clockwise or counterclockwise, you put in the loop currents. Next is to express branch currents in terms of loop currents. And so you can see, for example, my half amp loop, which was called X previously. Of course, it made sense to go clockwise because the half amp comes up on the left and then down from A, B, C to complete that loop. But for Y and Z, I just chose one clockwise, one counterclockwise. So if we look at I1, for example, I1 goes down through the 5 ohms, and we can see that I1 consists of a half amp coming down from A to B, and Y coming also down from A to B. So I1 is a half plus Y. But if we look at I3, for example, I3 comes down, and that is consistent with the half amp coming down through the 3 ohms. But Z through the 3 ohms is coming up. So it's a half minus Z. And you can convince yourself of these other linear combinations that give branch currents in terms of loop currents. So now we write our KVL or loop rule equations, and these are very similar to the KVL equations we wrote earlier. We only have to write them for loops Y and Z. And the difference is, instead of showing the branch currents, we show the linear combinations of the loop currents. And now we solve for the loop currents. Now this is just a 2x2 system with only Y and Z unknown. We could use Excel or just solve this ourselves. And we get Y is 0.124 and Z is 0.244. Once we have those loop currents, we can solve for our branch currents. And once we have our branch currents, we can enter them in the branch table, and then we can go on to complete the branch table. So why don't we start with the volts for the resistors, because we have Ohm's law. And then we'll complete the node table. Now, just for a little variety, I'm counting node B as ground here. And again, as we saw earlier, if B counts as 0 volts, then, for example, the volts at A would be minus to plus, or plus the volts associated with the 5 ohms, which was 3.12 volts. So that's the node voltage at A. And you can convince yourself, for example, the node voltage at E, starting at ground B, we would have a decrease in the volts across the 16 ohms. So minus 5.888, and then plus the 10 as we go from D to E, and that would give us 4.112. So our node table is complete. Now that our node table is complete, we can find the volts associated with the half amp supply as the difference in node voltages A and C. So if I take 3.12, the node voltage at A, minus negative 0.768, the node voltage at C, that then is 3.888, the voltage associated with that current source. So our node table looks different than before because we chose a different ground, but our branch table has the same values. We can calculate powers again with the same result, that the total power supplied equals the total power delivered. On to nodal analysis. Now for nodal analysis, we don't have as much of a setup as we did with branch current analysis and loop analysis. We really take it back to where we identified the nodes in the circuit. And I'll just put a node table here, and to have a little variety, I'll choose node D as ground. So node D counts as 0 volts. Notice then as I go from D to E, I'm going minus to plus, and that would be then plus the 10 volts. Not showing the 10, but it's the same values as before. Right, so 2 of the 5 nodes have known volts. D is ground, 0 volts by definition. E then is 10 volts more, and those are shown in the table. Now, how many equations and what kind of equations do we write? Well, here's again a side-by-side comparison of our methods, and you'll see that for nodal analysis, we only write junction rule equations. We don't have to write any loop rule equations. And we actually take the total number of nodes, 5, subtract 1 for ground, and we can take advantage of that known 10 volts, subtract 1 for the known voltage source, and that leaves us with 3 equations. So there are 3 equations to write, and they are of the KCl variety, and we basically write 1 equation per unknown node. With our choice of D as ground, that makes E 10 volts. That's A, B, and C are the 3 that are unknown. Now, the way you would write these equations is KCl is the current law or the junction rule. I normally like to write the equation as a series of currents that are leaving the node. My only exception here is my half amp is definitely entering node A. So I have the half on the right as entering, and the 2 terms on the left are leaving. So A minus B would be the volts across the 5 ohms. Divide by 5 ohms, that's Ohm's law for current. Right? So A minus B over 5 represents the current going from A to B through the 5 ohms. A minus E, remember E was 10, so A minus 10 over 8 is the current leaving node A through the 8 ohms. And that's our first equation. Now for our second equation, it's not involving the known half amp, and I like to write my terms as if the current is leaving. Whether or not it's leaving or entering, I write the term as if the current is leaving, because we don't know what the current is doing at this point. So it's easier to just say, for the node you're working on, B minus A over 5, that's the current going from B to A through the 5 ohms. Next, B minus D, remember D is 0, so B over 16 is leaving junction B, going over to node D. B minus C over the 3 ohms. That's the current going from B to C through the 3 ohms. Again, all of these terms can be positive, but it's okay to write the term as if the current is leaving the node. Junction C, we have the half amp leaving, that's 0.5, and then the other 2 terms, we take the node we're at, C minus B over 3, and then C minus E, which is 10, C minus 10 over 20, and that equals 0. So we have 3 equations and 3 unknowns. We can either solve them ourselves or use Excel or other software, but I get these values for the node voltages. So nodal analysis, we completely solve the node table first, and then we complete the branch table. So we can get the volts associated with each component in the circuit as a difference in node voltages. We also can know the current directions by which node voltage is higher. Let's look, for example, at the 5 ohms. Right? The node voltage at A is 9.008 volts. The node voltage at B is 5.888. Right? So 9 is greater than 5.888. So the current must come from higher volts to low volts through the resistor with a voltage decrease from plus to minus. I can get the volts associated with the 5 ohms as the difference in node voltages A and B. So 9.008 minus 5.888 is 3.12. And again, I can do that for every component in the branch table. I take a difference in node voltages to get the volts associated with that branch. In the branch table, though, we would always have positive values. Now, for the resistors, we can get the currents from Ohm's law, and then for that case of junction D, we know that the current in the 10-volt supply has to be the same as the current in the 16 ohms, so I can just copy down the 0.368 amps from the row with the 16 ohms down to the 10-volt supply. I can calculate powers as before, and we now have a complete solution. In summary, this flowchart shows from start to end 3 pathways to solving circuits based on Kirchhoff's rules: branch current analysis, loop analysis, and nodal analysis.